All right, today's lesson is all about sound waves. We've been studying about waves, and now we're going to sort of focus in on specific kind of wave, and that's sound waves. For this lesson, you're going to go ahead and set up your notes Cornell style, like you normally do. You're going to have a narrow column on the left and a wide column on the right. You're going to use your left side for any headings that I might use, or you could write down questions. We talked in class about how you can use that left column to write questions that you have as you're watching the podcast, and I'm not there to answer your questions right then. You can just jot that down in the left side column, and then when you come back to class next week, you can ask that question during class. The right side of the page you're going to, of course, use for your notes, and then don't forget to save space for a summary at the bottom of your page, and put the date in the top right hand corner, because that's always important to go back and see whatever it was that we did that day. The focus of today's lesson is about sound and how sound waves move through the air or through other kinds of substances, and how sound is produced. By the end of this lesson, you're going to be able to explain how sound is produced, describe how it is that sound travels through, in this case through the air, and reaches our ears, and you're going to be able to use what we know about particles in the air and in water and in solid objects to explain how sound moves. Now, this next part is a little bit of review over what we've talked about the last few days. You don't necessarily have to write this stuff down because you already have notes on this. But remember that waves transfer energy. They're not carrying matter, but they're carrying energy. But they have to travel through matter sometimes. And there are two types of waves. There are transverse waves and longitudinal waves. We had a lab today using slinkies, and so you got to see that firsthand. But transverse waves, remember, are waves in which the motion of the wave medium is perpendicular or at right angles to the direction of the wave. So transverse waves, the particles are moving up and down as the wave travels in one direction. Longitudinal waves, remember, in this case, the motion of the wave medium is in the same direction as the wave. So the particles are moving back and forth this way, and the wave is traveling in basically the same parallel direction. At this point, you probably haven't written any notes yet, but now would be a good time to start. The first main question for you to write down: how is sound produced? And you need to know that sound is produced, first of all, it's a longitudinal wave. It's carried as a longitudinal wave. And that the wave medium is going to be particles. Might be particles of air, might be particles of water, or even some other substance, even solids. It always starts from a vibration. Remember, a wave is a disturbance. In this case, sound starts through a vibration of some kind. So if you look at this diagram, you kind of have three steps to sound passing through the air, or sound waves passing through the air. Remember, you have air molecules. An object, in this case an electric guitar, makes a sound by vibrating. So you pluck the strings of the guitar and the strings vibrate. The vibration of the strings are going to set the air molecules vibrating because they touch each other. So the vibrations of the air molecules now are going to pass through the air here in step 2, causing air molecules to vibrate all along the way. So this little particle pushes on this little particle, and it pushes on this little particle, and so you have this wave that's generated through the air. And remember, it's a longitudinal wave, so it's compressions. The air is compressed together, and then there's a rarefaction where they're spreading apart. And then it's compressed together again, and then it's spreading apart again. And this wave travels through the air in all directions. Eventually, the vibrations, or this wave of vibrations, is going to make its way to your ear, or maybe someone else's ear. And at that point, it's going to vibrate a tiny little membrane deep inside the ear called the eardrum, or the tympanic membrane, and it's going to jiggle that membrane, and then there's a whole lot of stuff that goes on inside the ear, but eventually it is interpreted by your brain as some kind of a sound. Now at this point, I want you to really think about what I just said. That sound is traveling through particles. In the case of, for instance, my voice, you're hearing it through the air. although sound can travel through other kinds of particles. But I don't know if you've ever heard of this movie. It's kind of an old one. But the tagline for this movie was, "In space, no one can hear you scream." I want you to think about what that movie tagline means. Okay, maybe we can talk about it in class, but this is actually scientifically a valid statement. In space, no one can hear you scream. Think about why can't people hear you scream in space? And it's because, of course, there's no particles. Space is a vacuum. If there's no particles, sound cannot be passed along. Now, sound travels through particles that are vibrating, as I've said. I want you to think about what the particles look like in a solid, liquid, and a gas. We studied this earlier in the year. In a solid, the particles are all closely packed together. They are vibrating, but they're very, very closely packed. In a liquid, they're free to move around. There's fewer of them. They're not quite as packed. And then in a gas, of course, they're spread out very far apart, and they're zooming around. Now, because of that, sound travels fastest through solids. Okay, the particles are closer together, and so the vibrations are more easily passed along from particle to particle. So we don't usually think about sound passing through a solid object, but if we could measure the speed of sound in a solid and compare that to how fast the sound is traveling through a gas, we would find out, of course, that the sound would get there a lot faster through a solid object. The other thing to think about is, even with a gas, the temperature can affect how fast the sound travels. So think about in a gas at a warmer temperature, the particles are moving faster, so they're going to pass that sound more quickly. So warm air can send sound more quickly. The speed of sound is faster in warm air than in cold air. Now, I thought this was kind of fun to think about. In air, the speed of sound is about 330 meters per second, and that's about 761 miles per hour. In water, sound travels at 1,500 meters per second, and look at this. It's over 3,000 miles per hour. If you could measure that, of course, people can measure the speed of sound, but in water, so much faster. And then in a solid object such as wood, look at this, 13,332 miles per hour. Much, much faster in a solid object than in a gas. All right, everybody say, "Aww." All right, in addition to the speed of sound, you need to understand a couple of different things about sound quality. One is pitch, and the other is sound intensity. The pitch of a sound is the highness and lowness, and I don't want to, hurt your ears with my bad singing, but, high by oh and low by oh. Okay, that's what I'm talking about, the high or low of a sound. It relates to the frequency of the sound wave, and remember, frequency and wavelength are related, so it also relates to the wavelength of the sound wave. But pitch, the highness and lowness of a sound, relates to, it is the frequency of the sound wave. Likewise, intensity is the loudness or softness. So soft like as in a whisper, loud as in a scream. That relates to the amplitude of the sound wave. So even though sound waves are longitudinal waves, sometimes it helps to understand by looking at a drawing like this. Understand these are transverse waves, but this can kind of help us to understand it. If we were talking about a very soft sound with a high note, it might look something like this. The same high note, but a louder sound might look like this. Okay, the amplitude is higher. Likewise, a soft sound with a low note might look like this, and then a louder version of that same note would have a higher amplitude. Now, you don't necessarily have to write this down, but I think it's kind of fun to talk about the audible range of frequencies. For instance, the range over which we can hear. For human beings, the lowest frequency we can hear, the lowest tone we can hear is about 20 hertz. And then we can hear up to 30,000 hertz. Remember that cycles per second. When we're little, when we're young children. But as you get older, even you are getting older, the frequency that you can hear, the high end starts to drop off. Okay, so probably at your age, you might be still hearing around 20 to 25,000 hertz. But as you get older, You're going to be able to hear less and less of those high tones. So this relates to if you've ever heard of the mosquito ringtone on the phones. I know we may have talked about it already this year, but the mosquito ringtone is on this high end of frequencies, and older people generally can't hear it. I can't hear the mosquito ringtone. But of course, some students, some children can't hear it either. It depends on your hearing range, and everybody's different. And make sure you know that some adults can hear it. But it's kind of fun to talk about that mosquito ringtone because it really demonstrates this audible range of frequencies. It's also fun to talk about the audible range for other animals. Again, you don't have to write this down, but I just thought it was kind of fun to talk about. Dogs can hear up to about 45,000 hertz, and of course you've probably heard of something called a dog whistle that we can't hear at all, but it works for dogs, and probably it doesn't sound like something they want to listen to, I wouldn't think. It's probably a really harsh kind of sound. Mice can hear up to 91,000 hertz, but look at this, they can't hear down below 1,000, which means some of our human speech and things, maybe they aren't hearing, I don't know. Then bats can hear up to 110,000 hertz, which is crazy. This is a beluga whale. Beluga whale, this one here, beluga whales can hear up to 120,000 hertz. And then everyone's favorite, the chicken, can only hear up to 2,000 hertz, so they can't hear those high tones at all. Everybody say, "Aww." Okay, so we talked about the audible range of frequencies, and that relates to pitch, the highness and lowness of sound. But there's also an intensity scale. There's a range of intensities, and I would like to talk about that as well. That's going to be the loudness of the sound. The unit for pitch or for frequency is hertz. The unit for loudness or intensity is the decibel. You probably have heard of that before, decibel. And there's a little bit of a chart here, but the next slide I want to show you in more detail. So here, this gives you an idea. Like I said, you don't have to necessarily write this down, but it's kind of interesting. The definition of 0 decibel is human threshold of hearing. So anything at 0, we can't hear it, but just above 0 is right where we can start to hear it in terms of loudness. 20 decibels is like a rustling leaf, so maybe you're just outside and it's completely quiet and all you hear is the rustling of the leaves. That would be about 20 decibels. A whisper, depending on who's doing the whispering, some of you don't whisper very quietly, but a whisper is about 30 decibels. Normal conversation when you're just talking with your friends is about 60 decibels, 50 to 60. A vacuum cleaner is up to about 80 decibels. Your music players, that you wear your little earphones, maybe it's an MP3 or maybe it's an iPod, your music players are about 100 decibels, but some of them I think can go higher than that. You really have to protect your ears and be careful how loud you listen to your music players. Go into a rock concert, about 120 decibels. If you're near where aircraft are taking off, like if you're at the airport right where they're taking off, it's about 130 decibels. If you shoot off a gun near your ear, that's 140 decibels, and you can see here that at that level, that's permanent hearing damage can occur, and that's why if you've ever been to the gun range, you see that people are wearing headphones, noise-canceling headphones so that their ears are protected. It's very important not to ever shoot off a gun, or even really rock concerts. I would recommend that you wear some kind of protective earwear, maybe a little earphone that no one can see, because once you lose your hearing, once you damage your hearing, you're never, ever going to recover that. I don't know if probably Mrs. Napoles taught you about nerve cells, and how they cannot be regenerated. Now, new research has been making progress over the last few years, and there may come a day when they really can get nerve cells to regenerate. But at this point in time, we don't really have a way to get them to regenerate, and once they're damaged, you never get them back again. And so listening to those really loud sounds over your lifetime can end up in deafness, and you definitely don't want that. All right, we're almost done. The last thing I wanted to talk to you about, and I do want you to write this down, this is about sound absorption. I think you noticed on our learning scale that understanding how waves are absorbed is one of the things you really need to understand. And absorption is the transfer of wave energy into the medium. Okay, the wave is taken in by the medium. Usually a lot of that sound energy gets converted to heat, okay, or thermal energy is the more proper term for that. It gets converted into thermal energy, as a lot of energy does. And some materials, in terms of sound absorption, some materials are better at that than others. And we call that sound insulators or sound insulation. And this picture here is a picture of a soundproof room. They often use rooms like that to do recordings, like a recording studio would have soundproofing in it, or maybe something's going on where they don't want you to hear what's going on, like those TV shows or something. They have these soundproof rooms. It kind of looks like it's made out of egg crate or something, but that's what that's talking about. All right, I'm done. It's only 15, gosh, we're almost 16 minutes, but I appreciate your time, and we're going to talk a lot more about this stuff next week after on Thursday, and I really hope you have a great 3-day weekend.
Made with Doodlecast Pro.